Hello and welcome to our discussion about the vector space and the vector subspaces. In this video, we are going to identify the different types of sets that will classify into a vector space and the subsets of this vector space that will classify into a subspace. For our first definition, we have here the definition about a vector space. A vector space V is a set on which the two operations are defined, and these operations are addition and scalar multiplication. So this particular set V will be considered as a vector space if each of these following 10 axioms will be satisfied by the elements of V, U, V, W, and the scalars C and D. So the first five set of axioms is about the property of the addition. So you have there the first one is that the sum of two elements of V, U plus V, should also be an element of V. That is the closure of the set under addition. We also have the sum of U and V should be the same as the sum of V and U, which is about the commutative property of addition. The sum of U with the sum of V and W should be the sum of U and V with W, which is about the associative property of addition. And that your set V should have a zero element called as the zero vectors, for which any U in the set of V, we have there that U plus that zero should be equal to U, and that is what we call the zero element is what we call as the additive identity of V. And that for any U in V, there should be another vector in V represented by minus U, so that the sum of U with and minus U should be the zero element of V, and minus U is what we call as the additive inverse of V. And for the second set of axioms to be satisfied is that scalar multiplication is closed under the set V, that is the product C with an element U of V should also be in V, and that the scalar multiplication distributes over the sum of elements of V, that is C times the sum U and V should be equal to the sum of CU and CV. Also, the element of V distributes over the sum of scalars, that is the sum C and D times U should be equal to the sum of C and U and D and U. Also, that the scalar multiplication is associative, meaning to say that we can consider the scalar product of C with the scalar product du as the scalar product of CD with U. And there should be an element 1 in the set of scalars such that 1 times any element of U should just be the same as U. Any set of axioms, or any set that satisfies these properties or axioms, is what we call as a vector space. And the elements of this set will be named as vectors. So our first example would be the set R to the n. This is the cross product of n real numbers with the standard operations. So the standard operations being referred to is the component-wise addition and the scalar multiplication. The set of all ordered n tuples of real numbers in Rn, which is this one, V, is equal to the ordered n tuple V1, V2, V3 up to Vn, with the standard operation is a vector space. So in order for us to prove that it is indeed a vector space under the standard operations, we need to show that R to the n satisfies all the 10 axioms. And this is already verified from our previous discussion in chapter 3.1. So just to make a short recall about these properties, let us just do for n equal to 2, and let us go back to these properties. If your U and V would be, let us say, U is equal to U1, U2, and V is equal to V1, V2, and this should be elements of R2 because there are two components of our elements U and V. If we're going to find the sum U plus V, it should be U1 plus V1. So the sum is equal to U1 plus V1, U2 plus V2, And since U1 and V1 are elements of R, it would make that the sum U1 and V1, same with U2 V2, should also be an element of R, so that U1 V1, U1 plus V1 and U2 plus V2 should be an element of R2. And this we can commute that is as to V1 plus U1 and V2 plus U2, since V1 and U1, V2 and U2 are elements of R, and addition is commutative in with respect to the set R, so that we can have U plus V is just the same as V plus U. For the same property of associative property of real numbers, then we can also use the associative property to, to show that this vector addition is also associative, no? Considering we have a third vector, W1 and W2. So this sum right here would just be a vector of the form U1 plus V1 plus W1, then U2 plus V2 plus W2, and then you can just associate these elements to whatever pairing you want, because this is just these are just elements of R, and addition in R is associative rather. And there is a vector called 0, 0, the 0 vector in R2. We are referring this as the origin in the R2 plane, wherein for any vector u, so let us just choose this particular value of u1 plus 0 would just be u1, u2 plus 0 would just be u2, so that u plus 0 would just be u. And for this particular vector u, there is a vector negative u, which is negative u1 and negative u2, for which u1 minus u1 is 0 and u2 minus u2 is 0, so that this particular element is in R2, considered as the additive inverse of your vector u. Now for the scalar multiplication, c times u1 u2, c times u1 u2 would just be equal to cu1 and cu2, and a multiple of R, a multiple of an element of R is also an element of R, so that cu1 and cu2 is an element of R as well, so that this particular vector should be an element of R2. Same, if you're going to find for the sum of these vectors first, then you find its scalar product with C. It will be the same as finding the scalar product first, and then finding the scalar product first and determine its sum later on. So that is by this I am referring to this sum u1 plus v1, u2 plus v2. This is just the same as c of cu, that is cu1 cu2 plus cv1 cv2. These two are just the same, they are just equal. Also this can be easily verified, also this one, and any scalar or any vector u multiplied by the scalar 1 times u1 u2 will just be equal to u1 u2. So indeed, you can extend this length of ordered n tuple into n for you to show that Rn is indeed a vector space under the standard operations. So the standard operation is your component-wise addition and the ordinary scalar multiplication. Another example of a vector space is the set of all 2 by 3 matrices. So under matrix addition and scalar multiplication, this set is a vector space. Now, the elements of this space are vectors in this form A, which is a 2 by 3, a 2 rows and 3 column matrix. Note that the sum of any 2 by 3 matrix is just another 2 by 3 matrix, so that the sum would be closed under addition. And also for scalar, when you multiply a 2 by 3 matrix with a scalar, it would still be a 2 by 3 matrix, because we are just multiplying each entry of A by the scalar C, so that scalar multiplication is also closed under A is also closed under scalar multiplication. So it also follows that addition of matrices is commutative. It is also associative. And we also have the zero matrix for the additive identity, and the negative of your matrix for the additive inverse. So you can easily verify that the all the remaining 8 axioms will be satisfied by this vectors by this space of 2 by 3 matrices. Another one is the set of all polynomials of degree 2 or less, meaning to say polynomials of this form or polynomial degree 2 or less, or you could also include a x plus a naught, a1x plus a naught, and together with a naught, the constant. So this comprise this particular set of polynomials, not just polynomials of degree 2, but polynomials also of degree 1 and degree 0. So here, your considerations, if you're just representing these polynomials in this form, your a naught, a1, and a2 are real numbers with possibilities of a1 and a2 being equal to 0, so that this will be satisfied. If a2 is 0, this will be the case. If a1 and a2 are both 0, this would also be the case. If we're going to find for the sum of two polynomials, say p and q, with this corresponding representation, then the sum would just be, we are just combining the numerical coefficients of like terms. So combine the numerical coefficient of x squared, combine the numerical coefficient of x, and combine the constant. So a2 and b2 being real numbers is just another real number. You can represent this by c. You can represent this by c2 rather, and this can be represented by c1, and this can be represented by c naught, so that the sum p plus q is another polynomial of degree 2 or less. And the scalar, the possibility of having a degree less than 2 is that when we have b2 to be equal to the negative of a2, so that this would become 0, and then that would lead to a polynomial without the second degree exponent, so that it would just be of degree 1. But we are never going to a case wherein your degree will rise above 2, because we are not multiplying this degree, but rather we're just combining the numerical coefficients having the same powers of x. And the scalar multiple of p by the scalar c would just be, so that would be presented by c times p of x would be c a2x squared plus c a1x squared, a1x plus c a naught. So again, c being a scalar, an element of R, and a1 and a naught being elements of R also, this would mean that each of these underlined numerical coefficients would just be an element of R, so that c times p of x would be another element of this set of polynomials of degree 2 or less. So here the sum. Okay. So this shows right here that the set of polynomials of degree 2 or less represented by p sub 2 is closed under addition. Here is about the commutative property of adding your two polynomials now. So instead of having a2 plus b2, a1 plus b1, and a0 plus b0, since these are elements of R and some in R commute, so we can just commute this, each of this, and then you can have later on q of x plus p of x. So we are using here on the property that the sum of real numbers is commutative. There is a zero polynomial, no, in that case of the set of polynomials of degree 2, that is represented by 0 of x is 0x squared plus 0x plus, this is supposed to be 0, plus 0 for all x, meaning to say this is just 0 on that side. And if we're going to find its sum with p of x, it would not change, no? A naught plus 0, a1 plus 0, and a naught, a2 plus 0, and a naught plus 0. So it would just be p of x. And then we have here also the scalar c. This is for the seventh axiom. The fifth and the sixth axiom is already satisfied. The fifth is about the additive inverse. Now you can just negate a2, a1, and a naught. That would be your additive inverse, and it is also closed under scalar multiplication as shown in our as shown in here. No, so it is already satisfied axioms 5 and 6. So for the distributive property of the scalar over the sum of elements of P2, it would just be C times the sum would be A2 B2 x A2 plus B2 x squared, A1 plus B1 x, and A naught plus B naught. If we are going to distribute this C, it would be distributed over the sum. So that's we can have CA2 plus CB2 x squared, say A1 plus CB1 x, CA naught plus CB naught. And then you can just multiply x squared, distribute x squared inside, x also inside, and then regroup no according to the coefficients, numerical literal numerical coefficients, so that we will arrive with a form that looks like c times p of x and q c times q of x. So here, so we have regrouped those terms with a's and regroup those terms with b's and then factor out c. So this will be your p of x and you factor out c also in this one. So this will be your q of x. Here we have shown that the product, the scalar product c with the sum p and q is just the same as the sum of c and p and c and q. So what else needs to be verified? So you need to verify that it satisfies this one. So it is easy to show that C plus D times A naught out say plus D times A2 x squared, no? You multiply each of the numerical coefficients or each term of CP or rather of P by C plus D. It would be then broken down into terms containing C and terms containing D so that you will end up with C times P plus D times P. So similar for this one as well. It's easier to show. And also for the scalar, it would just be your ordinary number 1 multiplied to P. It would just be the same. So it will hold no for all. Rather, your set satisfies all the 10 different axioms, so that the space rather of second degree as the space of polynomial of degree 2 or less will be called as a vector space. And the elements and the vectors in this vector space are the polynomials itself. Now, the second example is a set of integers. The set of all integers with the standard operation does not form a vector space because simply it is not closed under scalar multiplication. Take note that your scalar is coming from the set of real numbers. Now, if you're going to pick, for instance, a scalar which is not a whole number, multiplying that to any integer, like for instance, 1/2 as your scalar, 1/2 times an integer 3 is equal to 3 halves, wherein 3 halves is not an integer. It's a rational number which is not an integer, so that your set of integers will not be considered as a vector space. The set of strictly second degree polynomial is not a vector space because it might fail with the closure of addition, considering the numerical coefficient of your second polynomial as the negative of the numerical coefficient of the first polynomial, the leading coefficient rather, no? Considering p of x as 2x squared plus 3 and q of x as negative 2x, wherein we are taking just the negative of the leading term, plus x minus 1. So the resulting polynomial would just be x minus x plus 2 rather, which is of degree 1. So that strictly the set of second degree polynomial is not a vector space, but rather the other one, the set of second degree polynomial or less, is a vector space because this is covered in the set of polynomials of degree 2 or less. This is a degree 1. The set of all ordered pairs of real numbers with the standard operation of addition and non-standard definition of scalar multiplication is not a vector space. So uh, this particular case now, if you are going to show that this is not a vector space, it would be helpful if you can visualize ahead of what you are going to do, because this particular set satisfies all other axioms of the set to be considered vector space aside from the last axiom. So here it satisfies all the first 9 axioms. However, it does not satisfy the very last axiom, which is about the scalar identity. Now, you can verify that it indeed satisfies all the first 9 axioms, but for the last axiom, instead of having 1 times x1 x2, by definition of its scalar product, because this is not your typical scalar product, this will just be 1 C x1, that is 1 x1, that is just x1, and then the second component would be 0. And this is not equal to your original vector x1 or original element x1 x2, so that we cannot have 1 times x1 x2 is equal to x1 x2, because x2 or the second component of the scalar product would be 0. So the 10th axiom is not satisfied. Therefore, this particular definition of the scalar product, or rather of operation in the set of all ordered pairs, will not make this set of ordered pairs into a vector space, just because of the definition of this non-standard scalar multiplication. So here we have we have these properties of scalar multiplication in a vector space. Let V be any element of a vector space, and let C be any scalar. Then the following properties are true. The zero scalar times any vector would give you the zero vector. So the difference there is that this one right here, the first zero is a scalar, an ordinary zero, while this one right here is a vector. So this could just be your zero as we know, and uh, this could be a string of several components, depending up to the dimension of your vector space now, to be a string of these vectors, of rather of these components. So it so happened that this becomes a vector because if you are going to do a scalar multiplication with 0 and a vector v has, let's say that v has n components. So you're going to multiply 0 to each of the n components of v, so that it would give us n components of zeros as well. Now, any scalar multiplied with a zero vector is a zero vector as well. So just imagine multiplying this by any c. It would just be 0 times c, 0 times c, 0 times c all the way, so that it would still be the zero vector. So this is a vector. And if c times v is equal to the zero vector, then either c is the zero or the vector itself is a zero vector. So this comes from these first two properties, and the negative 1 times v is the negative of v. So you negate all the terms, or all the components rather, of v, so that it will give you the negative of v. Now let us proceed to the subspace of a vector space and its definition. So in order for us to have a subspace of a vector space, it would just be the same as a subset of a set. But then in order for it to be classified as a subspace, it has to satisfy the 10 axioms satisfied by your vector space under the same operations, the same addition and scalar multiplication defined in V. So a non-empty set W of a vector space V is called a subspace of V if W itself is a vector space under the operations addition and scalar multiplication, which is defined on V. So for us to have a good idea about this, let us have this set W, which is the set of all ordered triples represented by x1, 0, x3, where x1 and x3 are real numbers. And let us show that this is a subspace of the vector space R3 with the standard operations. By the standard operations in R3, we're referring to the component-wise addition and the ordinary scalar multiplication. So we need to show that this particular set satisfies all the 10 axioms. And we need to show that it is non-empty. So note that 0, or W rather, is a non-empty set since it already contained the vector space 0, 0, 0. You can pick x1 and x3 as real numbers. You can pick 0 for the values of this, so that your set W is not an empty set. It's the very first idea to be considered when we are considering the subspace. It should be a non-empty subset of your set of R3, of your vector space rather. And 0, 0, 0 is also an element of R3, so that your W would be a non-empty subset of R3. Also, if we have these two vectors, x1, 0, and x3, y1, 0, and y3, these are vectors in R3, not yet vectors in W, because we are yet to show that W is a vector space itself. Then the sum would be, as in R3, x1 plus y1, 0 plus 0 is 0, x3 plus y3, and this should also be in W because x1 plus y1 is real, x3 plus y3 is real, being elements of real x1, x3, y1, and y3. Hence, your ordinary addition in R3 is closed under the set W. So W is closed under addition. Also, if we are going to multiply x1, 0, x3 with any scalar c, it would just be cx1, 0, cx3, and cx1 and cx3 are elements of R, so that this would still be an element of W, meaning to say that scalar multiplication of W is also closed under scalar multiplication. So the other 8 axioms will be verified as an exercise, and to give you a hint on how to do it, so it would be easy to show that the sum of two elements of R3 commutes, and it is also easy to show that it is commutative, or rather associative, and you'd consider the 0, 0, 0 as your zero vector and add it to any other vector in W, and you will be able to find out that the result would still be that particular vector or the particular ordered triple that you have chosen. And also there is that element negative u. No, the second component 0 would just be the negative of 0. It would not change, so it would still be 0. For the distributive property of scalar, it is also easy to show, and you have your ordinary scalar 1 to be considered as the scalar identity. So here we have a subspace test or a theorem wherein instead of performing all 10 axioms on the non-empty subset of your vector space, you only need to check on these two operations or two properties and show that your non-empty subset of your vector space satisfies this in order to show that that particular non-empty subset would be a subspace of the given vector. No? The theorem says that if W is a non-empty subset of a vector space V, then W is a subspace of V, if and only if the following closure condition hold. So the first closure condition is that if U and V are elements of W, then the sum U and U plus V should also be in W. And the second one is if U is in W and C is any scalar, then the scalar product should also be in W. So you're only to check these two, and if it is satisfied, then your subset, non-empty subset, is a subspace of the given vector. So this particular theorem says that it is enough to show that the closure of addition or the closure of the operations defined on V to be satisfied by W in order for W to become a subspace. So any vector space has at least two subspaces. So, and these two subspaces are what we call as the trivial subspaces, wherein these are the zero subspace containing only of the zero vector and vector itself, the vector space itself. Take note that a set is a subset of itself, right? A set is a subset of itself, so that a vector space is a subspace of itself as well. And the empty set is the empty set is a subset of any set. Here, we're considering that empty set, though there is an element, but it is just a zero subspace, wherein the element of that subspace is just the zero vector. These subspaces are what we call as a trivial subspace, and they are not the ones that we are looking after to. So the ones that we are looking for are the non-trivial subspace of your vector space. Now let us consider the set W, which is the set of all 2 by 2 symmetric matrices. So as I recall, symmetric matrices are those matrices X, or rather A, such that A is equal to its transpose. A is equal to A transpose. Let us show that this W is a subspace of the space of 2 by 2 matrices. So we have shown earlier that the space of 2 by 3 matrices is a vector space. It is also the same for the space of all 2 by 2 matrices. But then the idea here is that M sub 2 2 is just your ordinary vector space of 2 by 2 matrices. Meaning to say any matrix, any 2 by 2 matrix is an element of M sub 2 2. But what we are considering for W are those only that are symmetric matrices. So the operation defined on M22 would be the ordinary matrix addition and the ordinary scalar multiplication. So for us to show that, recall that W is not empty because W contains the identity element I22, or I22 rather, the 2 by 2 identity matrix, and this identity matrix is itself symmetric because it has only ones on the main diagonal and 0 on the off diagonal. Now we need to show that for any two matrices on W, it is closed under addition, and for any scalar, it is also closed under scalar multiplication. So let A1 and A2 be elements of W. Being elements of W means to say that A1 and A2 are symmetric, so that A1 is equal to A1 transpose and A2 is equal to A2 transpose. Thus, if we are going to find for the closure of A under addition, we need to show that the transpose of the sum A1 plus A2 would be an element of W. Indeed, not just an element of W, but rather it is just your A1 plus A2. No. As I recall, the transpose of the sum would just be the sum of the transpose. So that the transpose of the sum A1 plus A2 would be A1 plus A1 transpose plus A2 transpose, but A1 and A2 being elements of W means that these are symmetric matrices, so that A1 transpose is just A1 and A2 transpose is just A2. So what we have shown here is that the sum A1 plus A2 is equal to its transpose, so that A1 plus A2 is in W. A1 plus A2 is also symmetric. And it is of order 2 because we are adding matrices of order 2 as well. Now, for the scalar product, let us have C as to be a scalar so that we have the scalar, the transpose of the scalar C times A to the T would just be equal to C times the transpose of T. But A, transpose of A rather, but A being an element of W means that A transpose would be equal to A, so that CA transpose would be equal to CA. So what we have here, what we have shown here is that your scalar, your set W is also closed under scalar multiplication because C times A would just be a 2 by 2 matrix as well. Therefore, your of W is a subspace of M22. Now, to show that W is not a subspace of any larger set, we may show that W is empty. W is not closed under addition or W is not closed under scalar multiplication. So in order to show that a particular set W is not a subspace of any space, you're just going to show the negation of our theorem, or that our that does not satisfy any of the three conditions in this theorem, meaning to say it is empty, or it is not closed under addition, or it is not closed under scalar multiplication. That's the point of this statement right here. Now suppose that your new set W would be the set of all singular matrices of order 2. By singular, we mean those matrices whose determinant is equal to 0 or non-invertible. Show that W is not a subspace of M22 with the standard operation. So the same vector space M22 and different different subset W. Earlier we have there W to be the set of all symmetric matrices. Now W to be the set of all singular 2 by 2 matrices. So let us begin by showing that if A is, for instance, 1 0 0 1, 1 0 0 0, and B to be 0 0 0 1. So take note that the determinant of this matrix is 0 if we're going to use AD minus BC. This is 0 and this is also 0. But the sum of these 2 by 2 matrices would be component-wise addition for matrix addition. That is 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, which is an identity matrix. And your identity matrix is not non-singular, not singular, or it is non-singular. It is invertible. Hence, W is not closed under the ordinary matrix addition, which would mean that W is not a subspace of M22. So it fails to be closed under the ordinary matrix addition of M22. Also, we have here the intersection of two subspaces is a subspace of any of the two. Suppose that V and W are both subspaces, but whether not any of the two, but also a subspace of the original vector space. So to have a picture of this, let us have this schematic diagram. So the diagram looks like this ordinary Venn diagram, no? We have here the vector space U and the vector subspaces. It is considered now W and V are subspaces of the vector U. So our concern is to show that this intersection right here would also be a subspace of U, subspace of the vector U. Now to prove this one, note that V and W are both subspaces of U, so that it contains, both of them contains the zero vector being the additive identity of your vector space V and W, so that your intersection is assured to be non-empty. V has the zero vector, W has the zero vector, so that your intersection should at least have the zero vector within that one. So it is now shown that it is non-empty. To show that it is closed under addition, consider two vectors, v1 and v2 in the intersection of v and w. Then v and w are both subspaces of U, so that they are both closed under addition, under the vector addition of U. Meaning to say, if v1 and v2 being element of this intersection should also be an element of v and w separately, right? So that the sum v1 plus v2 is in V, being a vector space, a vector subspace, and v1 plus v2 is also in W, being a vector subspace. Meaning to say v1 plus v2 is a common element of V and W. That would mean that v1 plus v2 is also in the intersection. So what we have shown here is that v1 and v2 are two elements in the intersection of V and W, and their sum v1 plus v2 is also in the intersection of V and W, so that V intersection W is closed under addition. Now for the scalar multiplication, we have to show that V intersection W is closed under, that's the scalar multiplication. So let us pick a vector V in the intersection of V intersection W. So that would mean V is in V and V is also in W. V and W being vector spaces itself, it would mean that C times V is in V and C times V is also in W. Here, this statement means that C times V is in the intersection of V intersection W. So that means your intersection is also closed under scalar multiplication. And that shows that the intersection of two subspaces of any subspace is also a subspace of the given vector space.